Hi everyone, welcome back to another episode of Mr. Lewis Speedruns Your Homework. On this episode, I'm going to speedrun your homework. Also on this episode, we got a special guest. His name is Rupert. Come here, buddy. Rupert, come on. Come here. Come here. I know. Come here. Stay right there. Okay. This is Rupert, the physics dog. Loves physics. He's getting real... Where are you going? You don't want to do physics? He doesn't want to do physics. I can't understand why he doesn't want to do physics. Alright, so, anywho, I'm supposed to be doing my homework right now, which is reading a bunch of papers and writing some papers, but I don't feel like doing that, so I'm going to do your homework instead. It's a lot more interesting. Alright, so homework 2.3 speed. Let's take a look, see what we got here. Oh, is this a graphing one? Yes, it is. Oh, I love graphs. Graphs are the best. Alright. So, in this homework, we're graphing the motion of a car. We start a stopwatch when the car starts moving, so we can say that the car starts at 0 seconds. Alright, so... we've got a car, and let's say it is right here, and at 0 seconds it's sitting here, which is at 0 meters. Okay. There's a very long tape measure, blah blah blah, it goes on forever this way. Okay. And we are going to make a graph out of it. So, in section 1, the car drives with a constant velocity of 2.6 meters per second for 5 seconds. Okay, so the car is going to move in the right direction. It's going to move with a velocity equal to 2.6 meters per second. And it's going to do that for a time of 5 seconds. Okay, so since the car's velocity is positive, it is moving forward. The graph will have an upward slope. And that is because in our notes, you should know that the notes that we took the other day, positive slope, this is what we call positive slope. This means an upward slope is positive. That's what I'm trying to say. Upward slope is positive, flat, meaning 0 slope. 0 slope. Wow. This program does not like my L's. Okay, I'll have to do basic L's. This sort of slope is 0 motion, and a downward slope that is negative motion. Or when I say motion, I'm also talking velocity. I'm using those words interchangeably, basically. Velocity is the measurement of motion. And I say that it's a measurement of motion, not just the measurement of speed or rate of change, rate of position change, because velocity includes both speed, meaning it tells you how fast something's going, but it also includes direction. It tells you if it's going forward or backwards. So that's why it's the measurement of motion in its entirety, because it includes speed and direction, which it gives you like that's why velocity is better than speed, because speed just tells you how fast something's going, but it doesn't tell you if it's going forward, backwards, left, right. But velocity does tell you that. Okay, so anyway, in this section, the car travels a distance of blank. So if coming back here, we know that velocity is 2.6 meters per second. We know that t is 5 seconds, time is 5 seconds. We know that velocity is equal to distance divided by time. If we resolve this for distance, to do that we multiply t on both sides. Okay, that cancels over here, leaving us with distance equals velocity times time. Okay. So take these numbers and plug them into that equation, and we will end up with d is equal to 2.6 meters per second times 5 seconds. Okay, the seconds cancel out because there's one on top of a fraction and one on the bottom. 2.6 times 5. I don't know what that is. Do I have a calculator on here? Probably not. Okay, 13. So the distance we get at the end there is 13 meters. However, we got a problem. That's only 2 sig figs. So I need to write that as 13.0 to make that work. Okay. At the end of the section, the stopwatch will read, well, it's going to read 5 because it went for 5 seconds. Okay, so when the car, whoop, I just want the car. Bruh, get out of here. I just wanted the car, man. Bing. This is why Google's better. Oh my god. Oh no. You couldn't even search car. Bruh. That's really sad. Okay, anyway. This is a car. Okay, so the car started here at 0 seconds. It went all the way over here. It went 13 meters away. When this car got over here, the car moved from here to there. It moved 13 meters. It took 5 seconds to do that, and it moved with a velocity of 2.6 meters per second. So that's what's going on here. The car is literally just going straight. And the position at the end of the measuring tape is 13 meters. Okay, on a position time graph, the coordinates would be, okay, so time goes on the x-axis on a position time graph. So remember, on a position time graph, the x-axis, there's the x-axis, here's the y-axis. Time will always go on the x-axis, and distance will time is on the x-axis, distance is on the y-axis, always, always, always. There's some reasons for this. I'm not going to get into it, but it's always in this configuration. So time goes first. Okay, so we're going to put 5 and 13. All right, let's check our work to make sure that I submitted that all in the right way. Hello. All right, cool. You liked it. All right, so all right, I don't know why it's doing that. I'll just get rid of that for now. Okay, so section 2. So the car keeps going. So back to our car. All right, so this is all section 1. So the car is going to keep on moving, keep on trucking, right? So for 5 more seconds, so this is time 1, that's section 1, distance 1, velocity 1. For 5 seconds, time 2, for 5 seconds, the car travels a velocity for section 2 of 0 meters per second. So the distance it would travel, what's standing still because its velocity is 0, the graph would have 0 slope, it would be flat. In this section, it would travel 0 meters. At the end of this section, the time would read 10 because we did 5 seconds plus another 5 seconds. So at this point, the time total would be 10 seconds because 5 plus 5. And the car would be at a position of, well, it didn't go anywhere. Velocity was 0, so its distance, the distance it traveled in that section was 0. So the total distance is still 13 because it didn't move any further, so it just stayed at where it was. Gosh, it doesn't say sig figs. Okay, on a position time graph, those coordinates would be 10, 13. Go down to the graph, put the thing. Oh, I'm supposed to put that on. Okay, so let's do that. Let's do the graphing. All right, so I'm going to put down a segment. The first segment said put the first dot at 0, 0, and then the first coordinates are going to be time 1 and distance 1, 5, 13. Oh, perfect. Look at that. All right, so I need to lay down a second segment here. All right, segment 2. Point 1 needs to be the same as this because segment 2 starts at segment 1. So 5, 13. And segment 2 starts at, well, 10, 13. Okay, so there we go. So we can see the positive slope in the flat line. Okay, so far so good. Next section, car moves forward, so we're going to move the car forward again. All right, so car travels down, it ends up here. All right. So car moved forward again. This time, and I'll write it in a different color just to differentiate. This time it went for a velocity during section 3 of 3.4 meters per second. It went for a time during this section 3 of 3.4. No, oh my goodness. For 5 seconds. So what was that distance it traveled during section 3? All right, so we're going to use the distance is equal to time times velocity equation. So we take our time, which is 5 seconds, multiply that by our velocity, which is 3.4. Seconds will cancel out. 5 times 3.4 is 17. 17.0 meters would be our distance. Okay. All right, so at this point, we have traveled for 5, 10, 15 seconds. So the total time now is, it is no longer 10 seconds. The total time now is 15 seconds. And the total distance is 13 plus 0 is still 13. 13 plus 17, 20, 30. 30 meters total. Okay, so since this velocity is greater than it was at the beginning, this section of the graph will be steeper. More steep. The more velocity, the more slope. More slope means steeper. In this section, the car travels a distance of 17 meters. At the end of the section, the stopwatch will read the total time of 15 seconds. The car is at a position of total distance, which is 30 meters. On a position time graph, it would have the coordinates of 15, 30. All right, so let's see if that checks out. All right, so we're at 10, 13 for the segment before. Car. And the new one has to be 15, 30. Nice. You can see that's a bit steeper than that one. Perfect. Okay, so let's keep going. Section 4. Cars moving backwards. So, car puts it in reverse. It ends up back over here. Okay, car reverses. Whoa. Okay, write this in green as well to designate that as new. For this segment, which is segment 4, we travel for a time of 2 seconds, and we travel with a velocity in segment 4 of negative 4.2 meters per second. So that means we went a distance of, well, let's figure that out. Distance equals t times v. Our time is 2 seconds. Our velocity is negative 4.2. Okay. So it'd be negative, the s's cancel out. It'd be negative 8.4. I could have done that in my head. Why did I not do that? Meters. So negative 8.4 meters. Alright. So since this velocity is negative, the car is moving backwards. The graph will slope downward. In this section, the car travels a distance of negative 8.4 meters. And at the end of this section, it will read a time of, okay, so the previous total was 15. So we've traveled for 2 more seconds. So the new total of time is 15 plus 2, which is 17 seconds, because 15 was the old one. Alright, then we are looking for distance total after that. Alright, so we were at 30. We were at 30, but we're taking away 8.4 because we moved backwards. We got closer now, back to the origin. So this would be 31.6. Nope, 21.6. Okay. Be super embarrassing if I mess that up. Okay, so stopwatch says 17 seconds. This says 21.6 meters. Have coordinates of 17 and 21.6. Go down here, put in the graph. Okay, second 4. It's gonna have the same coordinates as this of 15 and 30, and then 17 and 21.6. Okay, and perfect. It came out down. That's great. Love it. Alright, section number 5. Last section here. Car drives with a constant velocity of 1.4 seconds for 7 seconds. Okay, so the car has decided to go forward again. So let's do bright purple. So now the car goes back out and goes in forward again, and so it's going to end up out here. Gonna make it small so I don't like cover all my work. Okay, so in section 5 we have a velocity in section 5 of 1.4 meters per second. We have a time in section 5 of 7 seconds. So to figure out the distance for section 5, we do distance is equal to time times velocity. Take our time of 7 seconds times our velocity of 1.4 meters per second. Nope, 7 and 1.4. I don't know where I got a 5 from. .8. Okay, so distance is equal to 9.8. Okay, seconds cancel out, leaving us just with meters. Okay. So distance is 9.8 meters, and that's in the positive direction. So our total time total, if the previous total was 17, so 17 plus 7 gives us 24 seconds. Yes, that's how math works. Okay, cool. In total distance, okay, it was at 21.6. Now we are adding 9.8 to it. 0.5, 22.5 plus 9, 31.5. $31.4. I'm dumb. $31.4 meters. I'm just gonna check my math real quick. There we go. Alright, cool. Nice. Okay, so this has a less velocity, so it's going to be a pretty shallow, less steep slope. The car travels a distance. What is the distance for section 5? That's 9.8 meters. The stopwatch is going to read a time overall, so that's total time, that's 24 seconds. It's at a position of 31.4 meters. And on a position time graph, this would have the 24 and 31.4. Okay, so the first point will have the same as these, so 17 and 21.6. 17, 21.6, and this one, the second one, will have to have 24, 31.4. Nice. And yeah, and so you see that's less steep. Alright, just go through, make sure all the points are filled in. Lovely. Alright, now let's check to see if we're right. Ah, wrong button. Mark it up. Woo! 100%, that's what we like to see. Alright, that was another episode of Mr. Lewis Speedruns Your Homework, and thank you, Rupert. Rupert? Roop? You want to say bye to everybody? Yeah? He's like, finally, we're done with the physics. Oh, don't get huffy. He's getting huffy. Thanks, bub. Thank you for all your help. Couldn't have done it without you.